Okay, guys, so I am going to find the derivative of each of these functions. If you want to try them for yourself, pause the video now, because I'm going to do them in this order, beginning right now. So let's see, the derivative of natural log of something is going to be like this. So I see natural log, I immediately write a fraction, and the numerator is always going to be 1. And then the denominator is going to be the original item in the parentheses exactly as you see it. It's an immediate copy and paste. Now, I'm going to multiply by the derivative of the inside. So now I'm ignoring natural log. I'm looking only inside the parentheses. I ask myself, what's the derivative of this? Well, power rule. 9 times 5 is 45. Preserve the base x. Diminish this by 1 to get 8. And then that would be it. Can I reduce this? Sure, I suppose that I can clean this up a little bit. 5 goes up into 45 9 times. x8 over x9. This is just like that, right? So you can clean it up a little bit. That is the derivative of this here. What about, let's go here now. So here, I have y prime equals. Now the derivative for natural log is going to be 1 over, copy and paste the original thing as you see it. Done. Now I'm going to multiply by the derivative of whatever is inside. So I ignore the natural log. I'm looking only here. I see a quotient. Let's hit this with the quotient rule. Okay, so the quotient rule says, let me go like this. The quotient rule says bottom times the derivative of the top, that's negative sign, minus the top times the derivative of the bottom, that's a power rule, that'd be 21x squared, all over the square of the bottom. So let's see, my first layer was natural log. This addressed the derivative of natural log. And then I multiplied by the inner layer. The derivative of this, well, this was a quotient, so I hit it with the quotient rule. Can this be cleaned up and simplified? Yeah, you can clean this up quite a bit. Like for instance, 1 over a fraction would be the reciprocal of that fraction, right? And then over here times, maybe I can go like negative 7x cubed sine x, like minus 21x squared cosine x, over, I suppose you can square that if you want to. And yeah, like I can take like a negative 7 from here. I can take out these x squares and I can reduce with this x to the 6th. You can do a lot of algebra if you want. I can do that if you want. Let's see. So let me leave this piece like this here. Because the more these you do, the more you see that algebra plays a huge role in your calculus. So let's see. So I believe that this is what we get here. That stayed the same. I took out a negative 7x squared from here and here. Do I believe what I have written down? I do. All over 49x to the 6th. Now in the top, that can be negative 49x to the 5th, along with the stuff in parentheses. And then I can go, the stuff in the bottom can be called 49x to the 6th times cosine x. And then the 49s knock out. The x to the 5 knocks out the 6, essentially. And so I'd be left with negative parentheses. X sine x plus 3 cosine x over x cosine x. So it seems like for this problem that I just made up, it seems like this would be the derivative of that. Let's keep going here. How about this one? Natural log of a square root, okay? Y prime equals 1 over, copy and paste. Okay, now I have to multiply by the derivative of this. Well, what is the derivative of that? A quick FYI. Remember that the square root of 7 minus x to the 4th is the same as 7 minus x to the 4th in parentheses to the power of 1/2. Yes, yes, yes. You could look at it as an exponent of 1/2 instead of as a square root with the radical. So I prefer to look at it this way, because now what I want is the derivative of this, because this is the same as that. But I think the derivative of this is easier to find. So the derivative of this would be a power rule first. So I have 1 there. We go 1/2 times 1, which is 1/2. I'm going to take away 1 from the exponent, and the base is preserved. It's still 7 minus x to the fourth, right? I'm not touching the base. Right now, I'm only doing the power rule. That's this guy. But now I'm gonna multiply by the derivative of the stuff inside, which would be negative 4x cubed. So you see, this here had 3 layers. It had the natural log layer, it had the radical layer, and it had the radicand, the stuff inside. It had 3 different layers. And yeah, this can be cleaned up like we did in the other example. I'll leave it there. You can just do all your fun algebra to clean this up. Okay, so now we want the derivative of this one. But before I do calculus, I'm gonna do algebra. I don't like how that's written. That really bugs me. So what I'm gonna do is instead of tangent squared x, I'm gonna write it tangent x quantity squared. And then I'm gonna go times secant 8x, like that. Okay, so now let's begin the calculus here. Let's find the derivative. It's a natural log, so it's going to be 1 over, copy and paste all that gibberish exactly as you see it. Nothing changes there. You just reciprocate the argument of the natural log. Copy and paste. So I've addressed this. I'm done with that. That's this part here. But now I have to multiply by the derivative of the stuff inside. Now inside, we have a product rule because there's 2 things. You see here in pink, this is one of the functions, and here in blue is a different function. If you want, we can call this one f, and we can call this one g. And do remember that your product rule says this. Your product rule for the derivative of an f times a g, 2 separate functions, you're gonna go f times g prime plus g times f prime. That is, it's the first times the derivative of the second plus the second times the derivative of the first. So let me open up a parenthesis, and then I'm probably going to close the parenthesis way back here because this is going to take a lot of space. So if this is called f and this is called g, product rule says this. So let me keep f, which is the first piece. That stays the same. Times. Now I need g prime, which is the derivative of this. So I ask you, what is the derivative of secant? The derivative of secant is secant tangent. The derivative of secant is secant tangent. So let me write that down. Secant tangent. But notice I didn't just write secant and tangent, right? It's secant of the thingy, tangent of the thingy. So the derivative of secant is secant tangent, but preserve the argument, the theta, okay? So this here represents the derivative of the secant layer, but now I have to multiply by the derivative of the inside, which was just 8. Okay, so very careful. So far this here is the fg prime. It's the original f times the derivative of that is all there. So now I'm ready for plus. And now I need g as is, which is secant 8x times the derivative of the first one. So what is the derivative of tangent quantity squared? Well, let's find the derivative of this. Let's find the derivative of this. Here I see a power. So let me hit this with the power rule. So the derivative of that is going to begin with a 2 in the front. I take 1 away from the 2, but I keep the base preserved. When I do a power, you don't change the base. That's still tangent x right now. Okay? So this piece that does the power, once you've done the power, which I did, then you can invade the parentheses. Then you could go inside the parentheses, and then you have to take the derivative of the stuff inside the parentheses. Now, what's the derivative of tangent? That would be secant squared. And then that would be it, because I would multiply by the derivative of the thing that's being tangented, if that's even a word. But since this is just x, the derivative of that inner piece would just be 1. So let me close this large parenthesis. Can this be cleaned up? Probably. I'm not going to do it. That's just algebra. The hardest part is setting this up here because it's messy. So this one involved a natural log layer, which is 1 over the thingy, and then multiply by the derivative of the stuff inside. But this was 2 separate functions, so it called for the product rule. So clean this up if you want to, but this is your derivative.